Welcome back to another AP Pre-Calc video. I'm Mr. Hibble. Today we're looking at our 2.9 notes. 2.9 is all about logarithmic functions. This is a new concept for us. This is a new idea. So let's just start by introducing it. One thing we know is that every operation in mathematics has exactly one inverse. Remember, an inverse is really just an opposite. It undoes something. Okay, so we know that everything has an opposite in math. For example, the opposite of addition would be subtraction. You could subtract 3 on both sides here to get the x by itself. So subtraction is the opposite of addition. The opposite of multiplication we know is division, right? You could divide by 3 on both sides there. We know that the opposite of cubing something would be taking a cube root or raising it to a fractional power, a rational exponent. But we know the opposite of a cube is a cube root. Notice that the x was the base of that and the 3 was the exponent. So now we have exponentiation, where you raise something to a power of x. 3 raised to the x power. Well, when x is in the exponent and you need to solve for it, that's not really possible unless you move it down somehow. How you can move it down is by taking what is known as a logarithm. A lot of the times people just reference this as a log instead of logarithm, but they do mean the same thing. A logarithm is just the opposite of an exponent. So if you needed to get rid of the base of 3 to get x out of the exponent, what you would do is take log base 3 of 3x. You would do that to both sides. Log base 3 of 7 is what you'd have over there, where the x would now be by itself. The opposites of an exponent are logs. Well, when you have these two things that are opposites, we can actually convert between their forms very easily. Logs and exponentials have equivalent forms. That means their form represents the exact same thing. If you were to graph these equivalent forms, you would get graphs that are the exact same. Exponents and logs have forms that are equivalent. Let's look at how to change those forms. One thing to note, if I have an exponent, let's say b raised to the a equals c. B is the base of your exponent. In order to change that to your log form, the b remains the base. Log base b. Notice b is a little subscript. Where the other two values then, in this case c and a, will change sides. These two forms are equivalent. B to the a equals c is the exact same thing, just in a different notation as log base b of c equals a. Let's look at converting these. Notice again the bases are the same. They both are b. So converting these then, I'm going to look at the base. In this case, I have a base of 3. That means the base of my log is also 3. The squared and the 9, those two parts then, we know that they kind of flip sides. So log base 3 of 9 would be equal to 2. You could do the same thing for b, log base 10, right? The base, switch the other 2, and you'd get something like this. But one thing that we want to note is when you have log base 10. Log base 10 is what is known as a common logarithm. Well, whenever you have a common log, you actually don't need the base of 10. It's just assumed it is there. So one way we could change this is log of y equals x. And now we have our answer. Same idea with the other ones. Log base r of w equals t. And this other one would be log base e. Switch the sides of those other two things, so 3x and y. One thing to note on this one, whenever you have log base e, Log base e is known as a natural log, so natural log of y. Log base e and ln, those are just equivalent for log base e. Again, ln is pronounced natural log. There's converting forms. You could do the same just in reverse now. You could change these to exponential form. Base stays the same. The other two parts switch side of our equal sign. Okay? And you could go through the rest of these. C, remember, log with no base means it's a base of 10. Natural log for part D means it was log base e. So that means I would have e to the fourth equals c, and so on. Okay, that is logs and just changing forms. The reason you might need to utilize this at times is when you're solving different logs, or maybe you are evaluating, you're just trying to simplify them. Well, if you're ever evaluating a log, what a log actually asks you to find is this phrase. Whatever the base is, for example, let's look at a. What I would do is I'd think about the base. The base is 2. And I would want to ask myself, 2 to what power equals the inside of 8? That's what a log is asking you. The reason it's asking you is if I were to change its form here, maybe I say this is equal to x. If I were to change its form, it would be 2 to the x equals 8. That is 2 to some power equals 8. What I know is 8 is the same thing as 2 to the third. So that just tells me that x must be 3. If I look at b, 5 to what power is 25? Well, 5 to the second is 25. And you could start to go through these different parts. For example, if I looked at d, that is log of 100. Well, that would be log base 10. Is 100. So 10 to what power equals 100? I know 10 to the second is 100. So this must just give us a value of 2. Okay, and we could keep going through these different problems. Some of these are good ones to note. For example, E is a good one. Again, maybe we set up this as an equation. So 16 to some power must be 4. Okay, well, I know 16 and 4, those are related by taking a square root. So maybe what I can do here is take a square root of 16. But that means I need to remind myself, if you take a square root of 16, that's the same thing as raising it to the 1/2 power. So what I could end up finding is that x needs to be 1/2. 16 to the 1/2 is what gives you a value of 4. F is another good one, because if I think, okay, 3 to some power is 1. Well, raising it to a power to give me 1. Well, anything to the 0th power equals 1. So I know that x in this case would be 0. Other good ones to note, I believe these fractional ones are good problems. For example, H. H says we have 6 to some power is 1/36. So we need to remember our exponent properties then. Exponent properties, how do I get a fraction in exponents? Well, that would mean I take 6 and I raise it to some negative power. For example, I have 6 to the negative 1, that's 1/6. But I don't want 1/6, I want 1/36. That would mean I'd have to have 6 to the negative 2. 6 to the negative 2 would be 1/6 squared, which would be 1/36. I know in this case, this evaluates to negative 2. Other problems that are good, different problems like that, maybe J, 1/3 to some power needs to be 81. Well, 1/3 to the x, 1 to the x isn't going to do something, so I need the 3 to be up there as well. So maybe you rewrite this as 3 to the negative x equals 81. And now you can just think 3 to what power is 81 and make it negative. That's one strategy. There's a bunch of different strategies that might work. Well, if I were to raise this to the 3 times 3 is 9, times another 3 is 27, times another 3 is 81. So 3 to the 4th is 81, but I needed 1/3 to some power be 81. That means x would have to be -4 in this case. K and L are both good problems. 3/2 to some power equals 27/8. Well, if you raise 3 to the 3rd and 2 to the 3rd, you would get both 27 and 8 there. And L, another good one. 9 to what power equals the 5th root of 81? Okay, well, 5th root of 81, that would mean I have 81 to the 1/5. Okay, but I know that 81 is just the same as 9 squared. So maybe this is 9 squared to the 1/5, which is just 9 to the 2/5. So now I'd see that x is 2/5 there. Problems at the bottom should be quick. We know that logs and exponentials are inverses, so this is just y equals 6. Again, logs and exponentials are inverses, so that's just 7, and so forth going through those problems. This one would be ln of e to the -4, so then you just get -4. And log base 5 of 5, those 5s just kind of cancel and you get a value of 1. We'll talk about that property more in the future. That was our 2.9 notes, just introducing these logs.